All right, so let's talk the chemical structure of hormones. Chemical structure of hormones can be proteins, in which case you have these long chains of amino acids, and they're basically bound together in different ways, and they make these complex three-dimensional structures. If you think about it, that kind of does make sense, because push comes to shove, if I want a very specific shape to fit into a very specific receptor, this is kind of one of the easiest ways for me to do that. I can really make specific shapes, three-dimensional shapes at that, when I make proteins. You can also have these short sequences of amino acids called polypeptides. Most proteins are going to be hundreds of amino acids long. Polypeptides are very short. If you look here, this is only 9 amino acids long, and it's held together by a disulfide bond. Di means two, sulfide, sulfur. There's one sulfur, there's another. This is oxytocin, and it's a peptide hormone. It's a very short sequence of amino acids that are bound together. Now, derivatives of amino acids. So, what's a derivative? It means it's derived from that, right? So, a derivative of an amino, sure, why not? A derivative of an amino, my goodness, today is just not my day. A derivative of okay, take 4. If you derive a hormone from an amino acid, it's called a derivative. A good example of that are these little dudes here. Triiodothyronine right here and tetraiodothyronine. The base for this is actually tyrosine, one of the 20 amino acids. Tri, what does tri mean? 3, right? Iodo is referring to iodine. So you've got 1, 2, 3 iodines added to triiodothyronine. Tetraiodothyronine, here's my tyrosine, 1, 2, 3, 4. I've got 4 iodines attached to that. And literally, it is one single amino acid that I've altered. Now, you might be going, those sound very complicated. It's thyroid hormone. Thyroid hormone comes basically in 2 flavors, triiodothyronine or tetraiodothyronine. Now, another type of structure that we have for hormones is lipids. And you kind of already know this from when we were talking about lipids in chapter 2, when we talked about organic molecules. Testosterone is a steroid hormone. Steroids are actually going to be hormones derived from cholesterol, cholesterol being a lipid. Now, testosterone, estrogen, progesterone, these are all examples of, hang on, I just unplugged my computer that I'm using, so I need to plug it back in. So this is a lipid hormone. It acts completely differently than the protein or the peptide or the derived amino acids, but it is a hormone. It does work in the same way. And then finally, we have glycoproteins. Glycoproteins are going to be a combination of a protein and a sugar. Now you might go, okay, but we've got proteins. Why do we need proteins and sugar combinations? Well, it kind of depends. If you want your hormone to have kind of a longer shelf life in the body, you make it slightly different than what the body normally sees. What I mean is, if protein enzymes see a glycoprotein, remember glyco means sugar, it's going to go, ooh, protein, and try and go after it. But then it's going to see the sugar and go, whoa, wait a minute. If sugar enzymes see this, they'll go, ooh, sugar, see it, and then look at the protein and go, wait a minute. Now, I'm not saying that we never get rid of it and it's always around, because that would be a lie. But the fact that you've got this kind of complexity to it means that it'll last a little bit longer. Now, let's talk about the control of the secretion rate. How do we control secretion rate? This goes back to something that we talked about in chapter 1. It goes back to homeostasis. Okay? When we talked about homeostasis, we talked about two things that can influence homeostasis. We talked about a negative feedback loop, and we talked about a positive feedback loop. So negative feedback and positive feedback. These are examples within your endocrine system. If you want to read through them and you want to go through them so that you kind of have a solid example in your brain, that's perfectly fine. But I want to kind of go back a little bit more to basics. So when we talked about homeostasis, we said homeostasis was a set point suitable to support life. And one of the examples I gave you was temperature. I said, what's the perfect temperature for humans? And almost everybody in the class is like 98.6. Great. That's our set point as human beings, as Homo sapiens. What about cats? Anybody know? Cats like their body temperature about 101, 102, okay? So if you put them at 98.6, they're not going to do so well. By the same token, if I put you at 101 or 102, are you going to be feeling like, woo, yeah, this is the best thing ever? Probably not. So, with negative and positive feedback influencing hormone levels, let's talk about how that works. So if you look at my little graph here that I've drawn, this red line is going to be homeostasis. This is perfection. Okay, this is unicorns and dragons and the rainbows, okay? But if you look at the yellow rectangle is what we call the homeostatic window. Basically, what that means is, hang on, let me get a different color. If I'm here and I kind of come up or I kind of come down, as long as I'm in that yellow range, I'm okay. Yeah, I may not be 100%, but I'm not going to die either. That's the homeostatic window. The homeostatic window is we're within range. It's not going to hurt us. Now, where does this get dangerous? Well, this gets dangerous. Hang on one second. I want to change to a thicker. If we go way above this, or if we go below this window. When we get into these ranges is when people start seeing problems, okay? So for the sake of argument, let's talk negative feedback first. Negative feedback, when our body starts coming up into danger range, okay? Negative feedback comes in and it says, no, 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 you get back into your window. You're not allowed to be up there. Come on. And it gets us back to normal. Okay? So negative feedback maintains homeostasis. It decreases any type of deviation from homeostasis. When I'm in AP1 and I'm first explaining this, I explain it as this is the friend that when you go out, to the club and you say, hey, I'm only allowed to have 2 drinks. And then when you're at the club and you're having a great time and you say, hey, give me another beer, this friend goes, no, 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 no. You said you were allowed to have 2 drinks, and get you back into that safe window. Okay? It doesn't let you roam around. Okay? Everybody good with that? Now, positive feedback is different. Positive feedback in the human body is very limited because it pushes you out of that homeostatic window. So let's say that you start going this direction and you're not in that window anymore. Positive feedback says, yeah, just keep going. Yeah, keep going, keep going, keep going. And when it does that, it's basically taking you way away from homeostasis. Most positive feedback loops in the body kill you. Okay? The example that's on this page here and childbirth are two of the only examples that I know of that don't kill you. So when it comes down to it, negative feedback decreases the deviation from homeostasis. It tries to get you back to that red line. Positive feedback keeps pushing you away from that red line. So that's the basics of negative and positive feedback. And to be honest, that's how this works. Your hormones and how they're secreted and how they're controlled, it's basically either a negative or a positive feedback loop. Okay. So there are three major patterns of regulation for hormones. There's non-hormonal regulation of hormone secretion, nervous system regulation of hormone secretion, and hormonal regulation of hormone secretion. In other words, what mechanisms actually control when a hormone is released? There's this one, there's this one, and there's this one. So, as with everything in the human body, because nothing can ever be simple, it's going to be usually a lot more complicated than we're describing it. Some hormones are going to be in the cardiovascular system or the circulatory system at relatively constant levels. We always have this much. Kind of like the graph that I just showed you, there's that perfect amount. Some are just released in response to stimulation, and other than that, they're not normally there. A good example of that would be adrenaline. I don't have adrenaline running through my body unless something scares me, right? You shouldn't have your heart beating like a crazy person if you're sitting watching Dancing with the Stars. I mean, I know Dancing with the Stars is exciting, and now that Carol Baskin's going to be on it, killed her husband, whacked him, right? Now that she's on it, it might become exciting. I don't know. But technically, you shouldn't be releasing huge shots of adrenaline for that 2-hour-long show. I don't know, maybe it's going to be 1 hour this season. I have no idea. And then you have those that are released in a relatively constant pattern over time. So a good example of that would be the hormones that are released to control the menstrual cycle. Every 27 days, there is a pattern of hormone secretion to get the uterine lining built up, to get it ready to implant an egg. And then when it doesn't happen, then there's another series of hormone levels that are dropping that basically cause that lining to slough off. And then we start building it again every 27 days. Yes, on average, not everybody is in that same time frame, but just go with me on it. So let's talk about these. Okay. Non-hormonal regulation, nervous system regulation, hormonal regulation. Non-hormonal regulation of hormone secretion. That means these hormones are secreted in response to something that isn't a hormone. So usually we're talking about changes in extracellular concentration of a substance other than a hormone that affect the function of the endocrine gland. Best example, glucose. Glucose is not a hormone, it's sugar. Glucose gets released into the blood and it influences the pancreas to release insulin. Insulin being the hormone. This is the hormone, right? But what's controlling its release? Glucose is. Is glucose another hormone? No. It's just a chemical that is present that when it's present The pancreas says, oh, I need to release insulin now. So we call this non-hormonal regulation of hormone secretion because technically it's not a hormone controlling it. Second one, neuronal or neural control of endocrine gland. What does it mean? It means that neurons are the ones sending the signal to an endocrine gland to release the hormone. We just talked about this in the last chapter. Literally, we just talked about this in the last chapter. The adrenal gland. It is an endocrine gland. And when sympathetic nervous system, fight or flight, fires, that nervous signal goes to the adrenal medulla and causes it to release epinephrine or norepi, or a combination of the two. But the impetus to cause that release, the key to causing that release, the thing that causes that release is going to be a neuron. A neuron is sending a signal, so it's nervous system control over the release of that hormone, as opposed to non-hormonal, where it's just some random chemical causing the release of the hormone. Now let's talk about the last one. Hormonal regulation of hormone secretion. Yes, it sounds kind of redundant, but it does happen. Hormones can control the release of other hormones. So the control of the secretory activity of one gland by a hormone or neurohormone secreted by another gland. So we were talking about thyroid hormone when I talked about triiodothyronine and tetraiodothyronine. So let's talk about thyroid hormone, T3 and T4. T3 and T4 right there. T3 and T4 levels, okay, in the blood should be at a really specific level, okay? And when they're not, there's this negative feedback. I'm not at the right level, I'm below that window that comes up to the hypothalamus. The hypothalamus releases something called thyrotropin releasing hormone. So this hormone's level is causing the release of this hormone. Okay, that's one. Thyrotropin releasing hormone, TRH, actually travels down to another gland and causes the release of TSH, which is thyroid stimulating hormone. So what do you think that hormone stimulates with the name like thyroid stimulating hormone? Exactly. TSH goes to the thyroid and it causes the thyroid to release thyroid hormone. Okay, so TSH stimulates the secretion of the thyroid hormones. So we've got literally 3 hormones initiating the release of 3 hormones. Now, admitted, it's different how they do this, how they accomplish this, but it's still a hormone causing the release of another hormone. So you've got, like I said, non-hormonal regulation. Hang on. Non-hormonal regulation. Glucose causing the release of insulin. It's not a hormone. It's not the nervous system doing it. It's just a random chemical. You've got the nervous system causing the release of the hormone. The sympathetic nervous system gets kicked on. Last night on the news, I saw a story about a couple that watched a bear start charging people in a national park, I think in Montana. And the people were running and they're like, don't run. Yeah, fight or flight kicked in, right? So what happened? The sympathetic nervous system sent a jolt of information to the adrenal gland and said, release epinephrine and norepinephrine, nervous system regulation. And then finally, we've got that hormonal regulation. Thyroid stimulating hormone stimulates the thyroid to release thyroid hormone. So you've got a hormone causing the release of a hormone.